It's my great pleasure to introduce Peikai from the Michigan State University. We're very happy to have him, and he's going to speak for us about Iwasawa lambda invariant and Massey products.
Okay. Thanks for introduction. It's a great honor to speak here. So today I will talk about the Iwasawa lambda invariant and the Massey product. So you may not be familiar with these two concepts. So in the talk, I will define these two concepts. So first, in number theory, there is the classical question. If for each number field, we can have a class group. So the basic question is how the class group change if we change the number field based on some field extension. This question is too wild to have a uniform answer. There is no good answer for this question uniformly. But if we can have some restriction for this field extension, we can have some good result. For example, you can assume our number field, the field extension is degree P extension, or you have a cyclic extension, or you say your field extension is unramified outside some primes, or you can give some condition for the size of class group. You say P doesn't divide the size of class group. So under some condition, we can have some good result. We can have some statement about how the class group change. And in this talk, I will mainly focus on two results. I will mainly compare two different invariants that control the answer to this question. One invariant is called the lambda invariant, is from Iwasawa theory, and another is cup product and Massey product. This is from Galois cohomology. And roughly, my main theorem can say in some cases, we can compute the Massey product. We can compute the lambda invariant by using the Massey product. My main theorem builds the relationship between the Iwasawa lambda invariant and the Massey product. So we can relate these two invariants from different theorems together. So this is a rough version about my main theorem. So first, this is just the abstract nonsense. So I need to tell you what is Iwasawa lambda invariant, and then I tell you what is Massey product. So this is the remaining part of my talk. So first, we define the Iwasawa lambda invariant. So in Iwasawa theory, we don't consider just one field extension. So remember in the question I asked in a field extension how the class group change. So Iwasawa said instead of looking at just one field extension, we look at a sequence of field extension or tower of field extension. Of course, you need to have some condition for this tower of field extension. So for a tower of field extension, this type of tower of field extension is called ZP extension. This means for each two term, it's a degree P extension. And the Galois group of KL over K is a cyclic group, Z quotient PL Z. And the K infinity is the union of all K1, K2, and KL. So if we take an inverse limit, then the Galois group of K infinity over K will isomorphic to ZP. Iwasawa proves that for such ZP extension, if you have a ZP field extension, there are three constants, mu, lambda, and nu, such that when error is sufficiently large, the P part of the size of the class group is controlled by the three constants, mu, lambda, and nu. So here I use this notation to denote the P part of the class group. So class group is a abelian group, and I can take the decomposite and take the P primary part. And every element is annihilated by a power of P. I put them together. So it's a p part of the size of the class group is controlled by these three constants, mu, lambda, and nu. So people are, after Iwasawa proved this theorem, people are very interested to compute these three constants, the three invariant mu, lambda, and nu. And Iwasawa conjectures that for cyclotomic ZP extension, the first constant mu should always be 0. And it has been proved by Ferrari and Washington for a billion number field. For a billion number field, and mu will always be 0 for cyclotomic ZP extension. And in our talk, I will give some example in our talk. And in this talk, our mu will always be 0. So the interesting part is to compute the invariant lambda. So in our talk, we mainly focus on the invariant lambda. And after Iwasawa proved this theorem, people wanted to calculate some example. And at that time, most the case, so all the cases we know is lambda will always equal to 1. So at that time, people calculate a lot example, but for all these example, lambda is always than 1. But people think there should be some example, lambda should greater than 1. So people wanted to find some cases, lambda greater than 1, at least 2 or 3. So Gauss is a mathematician at that time, and he wanted to construct an example such that lambda is greater than 1. So here is the criterion proved by Gauss. So let K be an imaginary quadratic field, and K infinity over K is the cyclotomic ZP extension. Here, a cyclotomic ZP extension means you construct this extension. So for number field, you can always construct a field ZP extension. So some number field has a lot ZP extension. Some number field may have a few ZP extension, but they all have a canonical one. They all have a canonical ZP extension by adjoin the piece root of units, piece power root of units. They all have a canonical one, and this canonical ZP extension is called cyclotomic ZP extension. So, and we assume P doesn't divide the size of the class group, and P split in K. And he proved that lambda greater than equal than 2 if and only if we have such modular relationship. And here alpha is the generator of this prime, this ideal. So here prime null is the ideal in OK, and HK is the size of the class group. So if we raise the prime to the power HK, this becomes principal ideal. So alpha is one element in this principal ideal. Alpha is the generator of this principal ideal. Yeah. So Gauss criterion give us a way to see when this lambda will greater than 2, and he also constructs many examples lambda is greater than 2 by using this numerical criterion. And an expert of group cohomology can recognize this equivalent relationship is just some cup product. So by using the Poitet's duality, I can show the numerical criterion proved by Gauss actually equivalent to some cup product. Here, K is just one element in the H1. Alpha is the same alpha here, is a generator of this principal ideal. So I need to tell you, this character K will appear a lot. This character K is associated to the ZP extension. So I need to tell you the definition of the K. So first we let S introduce some notation. S is the set of primes about P for in the ideal K, in the number field K. And Ks is the maximal extension of K, unramified outside primes in S. So this just means Ks is the maximal extension of K, unramified outside primes above P. And GKS denoted as the Galois group Ks over K. And it is a fact. So you can construct a lot ZP extension, but every ZP extension is always contained in this case. So this means for any ZP extension, it is unramified out primes above P. So this is a fact. Every ZP extension is contained in KS. So we can define the character K is a homomorphism from the Galois group. First, you restrict it to the Galois group K infinity over K, which is isomorphic to ZP. So we need to fix one isomorphic. Here we need to fix one isomorphism from the Galois group to ZP. So we have a homomorphism from the Galois group GKS to ZP. K is a homomorphism from the Galois group to ZP. And since the action is trivial, the Galois group acts trivial here, so it's isomorphic to H1. So K is element in H1. K is associated to a ZP extension. If you have a ZP extension, you can always construct a character K. So here I transformed this numerical criterion into some cup product. So, but I didn't tell you why I wanted to transform this numerical criterion into the form of cup product. So next, I will tell you another classical result, and we will see the reason why I wanted to transform into the language of group cohomology. So let's look at another classical result, McCallum-Scherfis result. So mu_n denotes the group of nth root of unit. Recall that we call a prime P is irregular if P divides the size of the class group. So and also P is regular just means P doesn't divide the size of the class group. And if P divides the size of the class group, we can decompose the P part of the class group into the direct sum as with respect to the action of the Galois group. So you can imagine, so if we have a vector space, if you have a vector space and you have a matrix act on this vector space, then you can decompose the matrix space as the direct sum of some eigenspace. And similarly here, if you have a abelian group, here class group is abelian group. If you have a abelian group, you can, and you have some group act on this abelian group, you can also decompose this abelian group into the direct sum of some eigenspaces with respect to this action. So we decompose the Galois group into some small pieces. Here for these pieces, we have the invariant lambda. And for each smaller pieces, we can similarly define the invariant lambda I. For each pieces, for the I pieces, we can also define the lambda invariant lambda I. And McCallum-Scherfis result said for cyclotomic field, if you keep a joint to the p squared root of unit, p cube root of unit, and you can have a cyclotomic ZP extension. And we assume here we decompose the class group into some pieces, and we assume one piece is non-zero, and this means the element is annihilated by P. So we assume one piece is non-zero and is isomorphic to FP, and we fix one pieces. We need to fix one pieces, and you have some other conditions. Then for these pieces, lambda I greater equal than 2 if and only if this cup product vanish. Here, this alpha I is one element constructed from the ideal. The class group is constructed from some ideal, and lambda I is the invariant corresponding to that pieces. So we can decompose the class group into some direct sum of pieces, and for each pieces there is a lambda I, and for that pieces lambda I greater than 2 if and only if some cup products vanish. Okay, and this character K is the same definition. The character K is the same definition as before. Alpha I is one element construct from some ideal. And so for every case we know, in this setting up, for every case we know lambda I is always equal to 1. For every case we computed, lambda I is always equal to 1. So McCallum-Sherif's result means that since lambda I is always equal to 1, this means this cup product is non-zero. So this means there are some interesting cup products. So although as far as I know, although for this setting up, every cases we know lambda is always equal to 1, but there is no conjecture said lambda equal to 1. So I guess in this case, we still believe there may be some cases lambda is greater than 1. Yeah, even if every case we know, lambda is equal to 1, but we still believe maybe there are some cases lambda will greater than 1. Okay. Now we can put these two classical results together. So you can see for the first one key is the imaginary quadratic field, and for cyclotomic ZP extension. And under some conditions, we have the lambda greater than equal than 2 if and only if some cup product vanish. And for cyclotomic ZP extension, for cyclotomic field and for cyclotomic ZP extension, and similarly, lambda I greater than 2 equal than 2 if and only if some cup product vanish. This two theorem has been proved into different time and different method and for different field, but they both have the similar form. They both have a similar form, lambda greater than 2 and equivalent to some cup product vanish. So which motivates us to find some deep reason behind it. For the theorem are proved in complete different method. For the first theorem, the Gauss criterion, his original proof doesn't use any language in group cohomology. He just uses some classical number theory. He doesn't use any group cohomology language. And so they are proved by using different methods, but they look similar. And my results, my theorem give a unify these two theorem and explain this phenomena, and also give a generalization of these two theorem. And yeah, here, if we wanted to generalize this, so you can see for the left-hand side, if we want to generalize this, it's easy. We lambda greater than 2, lambda greater than 3, lambda greater than 4. We can generalize it very easily for the left-hand side. And then for the right-hand side, we have the cup product vanish. So we wanted to generalize the car product. So this means we need to find a generalization of car product. What is a good generalization of car product? So there are two generalizations for car product. One is Massey product, and another is generalized box type map. So in the remaining talk, I will explain these two generalizations of car product. So now our goal is to generalize the car products. Here, there are two ways to generalize. Here we introduce the first one, Massey product. So we think Massey product is a generalization of car product. And here I didn't give the definition of Massey products. I just give the motivation of the Massey product, give you a reason why we think Massey product is a generalization of car product. So here we have two characters. If you are given two characters, K1 and K2, since the Gauss group is here, G is any abstract group. In our case, we take G to be Gauss group, but when you define a Massey product, G can be any abstract group. And K1 and K2 are two homomorphisms from group G to FP. So we can form two representations, G to the GL2 FP. You just put the 1 in the diagonal and the character K and character K2 in the next diagonal. And we wanted to glue these two representations together. So you have the first representation, you can put it here, and you put your second representation here. We wanted to glue these two representations, but we don't have any element here. We don't have any elements in this star spot. So we wanted to glue these two representations. This means we need to put one element here. So we wanted to fill a spot here such that the above become a representation. Okay. We can fill a spot here such that the above become a representation if and only if K1 car product with K2 equals to differential phi, the negative differential. D is the differential. And this equivalent to the car product is 0. So this just means if your car product K1 and K2 is 0, then we can fill this spot and we can have a representation. And if your car product is non-zero, then we can't fill any element here such that this become a representation. So this gives us, this just tells us the car product is the obstruction for us to glue. If the obstruction, the car product is 0, then we can glue them. If the car product is non-zero, this means we can't have a representation. We can't glue them together. And generally, if we have a higher dimensional representation, here we only have a 2x2 matrix. If we have a higher dimensional representation and they are compatible in a certain way, and we want to glue them together, then Massey product is an obstruction for us to glue them together. Here, this compatible just means, so for example, when we try to glue two functions together, we must require them compatible in some way. If we want to glue two functions together, you must require in the intersection of their domain, they have the same value. So if you want to glue something together, they must be compatible in some way. So except you have a data in the H1, except the data in H1, you also have some extra data, and this extra data should be compatible in some way. Otherwise, you can't glue them. So if they're compatible in some way, then you can think, could we glue them together. Okay. So in this way, we can think Massey product is the generalization of car product. Okay. Before I introduce the second generalization of car products, we can look at the history of Massey product. So Massey product was first introduced by Massey when he considered the following node, the bromine bromine links. So here you can see from this picture, each two nodes are not connected with each other. Each two nodes are not linked, but these three nodes are linked in a non-trivial way. You cannot separate these three nodes without breaking them. So each two are not linked. So in knot theory, the car product is just the link number. The car product is the link number. Here, each two nodes are not linked, means the link number is 0, means the car product between each node are 0. So in this case, car product can't tell us some information whether this is trivial or not. And Massey said, if you consider the triple Massey product between these three nodes, then the triple Massey product is non-zero. Then this tells you this node is not trivial. Okay. Actually, there are also analogy between nodes and primes. So here, when you're embedding a S1, the node, into a Euclidean space, the behavior is similar to when you're embedding a spec FP into spec Z. So for this side, you have the singular cohomology. For this side, you have a etocal homology. The singular cohomology, the behavior of singular cohomology is similar to the behavior of etocal homology on the right-hand side. Yeah. And motivated by this, there is also a Massey product vanish conjecture proposed by Minek and Tan. In fact, when I learned Massey product, I first learned Massey product by learning the Massey product vanish conjecture. The conjecture said, for every field K, and for every prime P, and any integer n greater or equal than 3, and any character in H1, if the Massey product is defined, then it will vanish. So here GK is the absolute Galois group of K. So you can see there is some difference between his conjecture and our cases. So here he takes the GK is the absolute Galois group. But for us, our group is GKS. GKS is the maximal unramified extension. Sorry, maximal unramified out primes P extension. So we doesn't take the absolute Galois group. We have some ramification. Okay, and this is one difference. And we also have another difference here. In the conjecture, if your representation data are compatible, this means the Massey product are defined. Recall for Massey product, this is the obstruction for us to glue two representation together. So you have two representation and they are compatible, then you can define the Massey product. If the Massey product is 0, that means you can glue them together. If the Massey product is not 0, this means you can't get a representation. And so you have some data that are compatible. And the conjecture said if if your Massey product is defined, even if your Massey product is not 0, you can modify your data a little bit and make this Massey product become 0. So if you can define a Massey product, even if it is not 0, the conjecture said that you can modify it a little bit, and then the Massey product will become 0. However, in our case, I restrict to some specific type of the data. You can't modify your data. I will give you the data in advance, so you can't modify it. So this is one big difference. In our case, I will define so-called proper defined system, and so you can't modify this data. Okay. Now we can talk about another generalization of box type map. Sorry, another generalization for cup product. We wanted to generalize the cup product. Here is another way to generalize it. So let G be any abstract group. G is any group, and N is a normal subgroup such that the quotient G quotient N is isomorphic to ZP. And similar as before, we can define our character K as G to the map G quotient N and isomorphic to ZP. Here, we also fix one isomorphism from G quotient N to ZP. And we can view this K as one element in the H1 in the first comerge group. Then we can define the group algebra. We can define group algebra with the coefficient Fp. Since we have a profinite group, so we need to take the completion. So we actually get a complete group algebra, and we denote by omega. And as usual, we define I is the augmentation ideal. I is generated by sigma -1, and sigma is a topological generator of G quotient N isomorphic to ZP. Okay. So we can, everything is just a module, so we can form a exact sequence 0 to I quotient I square, omega quotient I square to omega quotient I. And when we have a shorter exact sequence, and we can always form a long exact sequence. If you have a short exact sequence and G act on this module, then you can have a long exact sequence. And the connecting map C1 from H1 to H2 is a cup product. So this is the fact. This is a fact. When you have a exact sequence, and in this way, the connecting map will be the cup product. So the cup product is a connecting map. In this case, cup product is a connecting map. So now we want to try to generalize cup product. And here we take such exact sequence, and cup product is a connecting map. So if we want to generalize it, the natural idea is we can take this exact sequence from IN quotient IN plus 1, omega quotient IN plus 1. So the previous page, so this case is just the 1n equals to 1, the case 1n equals to 1. And now we take n to be arbitrary integer. So we can have such exact sequence, and we define the generalized box type map as a connecting map from H1 to H2. And when n equals to 1, this just gives you a cup product. So when n equals to 1, you recover the cup product. So in this way, we think generalized box type map is also a generalization of car product. So now we have two generalization of car product. The first one is Massey product, and now we have a generalized box type map, and it is also a generalization of car product. We have two ways to generalize car product now, and in some cases, the image of the generalized box type map can be computed by Massey product. I want to, yeah, this means these two generalizations are not isolated to each other. This generalization, there in some cases, these two generalizations are related in some way. The image of generalized box type map can be computed by using Massey product. These two generalizations are connected in some cases. Okay. And in our case, we take G to be the Galois group. Recall that the GKS is the maximal unramified extension, maximal unramified outside prime P extension over K, the Galois group. And similarly for the GK infinity S, then G quotient N will isomorphic to ZP. And we have an exact sequence in this way, but we didn't directly take this exact sequence because we are in number theory case. So we want to twist it a little bit. We want to tensor it with mu p. Mu p is a piece root of unit, the group of piece root of unit. We want to twist it a little bit. We don't directly take this exact sequence and form a long exact sequence. We need to twist it a little bit. And if you tensor mu p, this is still exact because every module is flat. Every module is flat. So if you tensor p, it is still exact. You twist it a little bit, and we define the generalized box type map is the connecting map from H1 to H2. So it's the same as before, but we just twist it a little bit. So we define this. Here we define the connect map from H1 to H2 as our generalized box type map. Now we can state our main result. That K is a ZP extension, K1, K2, K infinity is a ZP extension, and S, as before, S is the set of primes about P for the field K. And we assume this ZP extension K infinity over K is totally ramified for all primes in S. So since S is a set of primes about P, this means this is ZP extension K infinity over K is totally ramified for all primes about P, for all primes about P. And we can denote the X is the inverse limit of S class group. Here I didn't take the class group, I take the S class group. So you can also take S class group, and you can also form the invariant, Iwasawa invariant mu and lambda. And further, we assume X has no torsion element. X is Iwasawa module, X has no torsion element, and H2 is isomorphic to FP. Then the Iwasawa invariant mu is 0 if and only if there exists some integer k such that the generalized box type map is non-zero for some k. And if mu is 0, then lambda can be computed in this way. So here, the above item is just some condition. The key here is if our mu is 0, if and only if there exists some integer k such that the generalized box type map is non-zero. And I didn't say anything about mu is non-zero. So if mu is 0, we can recover the information about lambda. If mu is non-zero, we can't recover the information about lambda by our strategy. So by using our strategy, you can determine when the mu is 0. And if you determine mu is 0, then you can recover information about the lambda. And if you find out mu is not 0, you can't see any information about the lambda. So in other words, the information about lambda is covered by mu. So if mu is not 0, you can't see any information about lambda. And if mu becomes 0, we can see some information about the lambda. Okay. And we can apply the theorem into the Gauss criterion, the same case as Gauss criterion, So recall in Gauss criterion, we have K is an imaginary quadratic field, and K infinity over K is a cyclotomic ZP extension. And P doesn't divide the size of class group, and P is split in K. So this is the same setting up as Gauss criterion. And if we assume lambda greater than n minus equals than n minus 1, then lambda greater equals than n if and only if the n-fold Massey product is 0 with respect to some property defining system. And this alpha is the same alpha as before. Here in Gauss criterion, it has an alpha. So this alpha is the same as Gauss criterion. And K is the character associated to the ZP extension we defined before. So this tells you if you have lambda greater than n minus 1, then lambda greater than n if and only if n-fold Massey product vanish. This directly generalized the Gauss criterion. Gauss criterion said if lambda greater than equals than n, Gauss criterion said lambda greater equals than 2 if and only if 2 for the car products vanish. This directly generalized the Gauss criterion. And you may feel strange why I write it this way, lambda greater than n minus 1, then lambda greater than n for the Massey product vanish. So you can think in this way, if we have this condition, this directly just means lambda is the minimal n such that the n-fold Massey product is non-zero. So directly by this statement, this statement is equivalent to saying lambda is the minimal n. Here I have the quoting mark for the Massey product because it's not the same as the min-x tens Massey product conjecture, the same Massey product. Here I need to fix the property defining system. I need to fix the data. You can't in their conjecture you can modify this data, but in my case you can't modify the compatible data because I fixed the property defining system. You have to have the property. So I have a quoting mark here. And similarly, if we apply the main result to Maclaurin-Sheriff's result, so recall in their setting up, K is a Q adjoint piece root of a unit. And you can keep adjoint p squares root of units, and you have a cyclotomic ZP extension. And if you fix the I and some other condition here, this is the same condition as in the Maclaurin-Sheriff's result, the same condition in the classical setting, the same condition. And we can have lambda I is the minimal n such that the Massey product is non-zero. And this alpha I is the same alpha I as before, constructed from the class group. These pieces corresponding to these pieces. Okay. So now we can talk about the idea of the proof. So by using Kummer's theory, we can connect the size of class group and the cohomology group. Here, you can see we have a S-class group, and it is related to the first cohomology group. And also the quotient of S-class group also related to the second class group. And so by using Kummer theory, we can relate the class group and the cohomology group. Then Lam, Liu, Sharifi, Beck, and Wang proved that the size of cohomology group can be controlled by the generalized box map. Here we have a filtration, here IN quotient IN plus 1. So we have a filtration of the second cohomology group. And here, if we can control the size of H2, GKS mu P, if we can control the size of this one. So the filtration is determined by generalized box map, the image of generalized box map. So in other words, if we can control the size of this, then the size of the filtration, the left-hand side, the size of the filtration is totally controlled by generalized box map. So if we can control the size of general box map, then we can control the filtration of cohomology group. Then we can get the size of the cohomology group. Then by the Kummer theory, we can get the size of class group. So this is the link. And they also proved in some cases, the image of the generalized box map is spanned by a Massey product. So here you can see we for Massey product first related to the generalized box map, and we can use this formula by relate the generalized box map to the size of the filtration, the size of cohomology group, and then we can use the Kummer theory related to the class group. So and here in my results, you can see the Kummer series, the class group here in the Kummer series, this is every element is annihilated by P. But in the Iwasawa theory, we want the P part of the class group. And here we only have the rank of the class group. This is not directly related to the P part of the class group. So the dedicated part is to relate to the P part of the class group with the cohomology group. Okay. Then we can summary the talk. So in the talk, I first explained the definition of Iwasawa lambda invariant. So Iwasawa lambda invariant can control the growth of the size of class group. And some classical results, the Gauss criterion and the Mackay-Sharif result tells us lambda greater equal than 2 if and only if certain cup product vanish. And so we wanted to unify these two classical results. We unify them together and give some explanation on why this phenomenon happens, and also generalize their results. So to generalize their results, we need to generalize the cup product, and the Massey product can be viewed as a generalization of cup product. So we have our main results is if you assume lambda greater than -1, I should put some assume here. If you assume lambda greater than -1, then lambda greater than n if and only if certain Massey product vanish. So in other words, this just means lambda is the minimal n such that the n-fold Massey product is non-zero. Okay. I stopped earlier. Sorry, I ended earlier. Okay.
No, it was perfect. Your timing is perfect, actually, Peikai. Thank you for a great time.